Hello, in this lecture we'll find out the length of line segment CB. In the drawing we have a semicircle. Inside this semicircle we have square DEFO. We know that the area of square DEFO is equal to 5 square units, and we also know that point O is the center of the semicircle, and we have to find out the length of line segment CB or chord CB. Okay, so first of all, we know that the area of square DEFO is equal to 5 square units. So you can write down that the area of square DEFO there's two square brackets is the sign for the area. The area of square DEFO equals to 5 square units, and we know that the area of any square is equal to the side squared. So the area of square DEFO that is equal to 5 square units, 5 square units is equal to the side of square DEFO squared. Okay, so we'll take a root out of this equation and we'll find out that the one side of square DEFO equals to square root of 5. So we can write here that FO equals to square root of 5 units, DF also equals to square root of 5 units, EO also equals to 5 square root of units, and DE equals to 5 square of units, or square 5 units. Okay. In the next step, we'll join points D and O by a straight line. But before that, we know that all the angles inside the square are right angles, therefore all those angles are right angles. This angle equals to 90 degrees. This angle it is also equals to 90 degrees. This angle equals to 90 degrees. And this angle it is also equals to 90 degrees. So in the next step we'll join point D and O by a straight line. You should remember that point O is the center of the semicircle. Okay, so here by joining points D and O by a straight line, we created triangle DOF. The triangle DOF is a right triangle because of the fact that this angle equals to 90 degrees. It is one of the angles of the square. So in the right triangle, triangle DOF, we can implement the Pythagoras theorem. So by PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So if we focus on the right triangle DFO, we can draw it again here. This is triangle DFO. We copy triangle DFO from the original drawing here. We have already found out that DF is one side of the square that is equal to square root of 5 units. FO is also one side of square. DOF and DEFO, this is also equal to square root of 5 units. The only missing side is the hypotenuse DO. So according to the Pythagoras theorem, we get that DF squared plus FO squared equals to DO squared. DF equals to square root of 5. So DF squared equals to the square root of 5 squared plus FO, it is equal to square root of 5. So FO squared equals to square root of 5 squared. That is equal to DO squared by Pythagoras theorem. Square root of 5 squared is 5. So it is 5 plus 5. That is equal to DO squared. So 5 plus 5 is 10. That is equal to DO squared. In the next step, we'll take a root out of this equation. And we get that DO equals to the square root of 10 units. Okay. DO equals to the square root of 10 units. You can write in the original drawing that DO equals to square root of 10 units. But what is line segment DO? Line segment DO starts from the center of the semicircle, that is to say from point O, and ends at point D, that is a point on the semicircle itself. That is exactly the definition of a radius. That is to say, DO is the radius of the semicircle. Likewise, what is line segment AO? It starts from the center of the semicircle and ends at point A, that is a point on the semicircle itself. Therefore, AO it is also the radius of the semicircle, that is equal to square root of 10 units. Likewise, OB, line segment OB, it starts from the center of the semicircle, that is to say from point O, and ends at point B, that is a point on the semicircle itself. Therefore, OB is also the radius of the semicircle that we have already found out, that is equal to square root of 10 units. Okay. Now we have a rule that says that the sum of the angles on one side of a straight line is equal to 180 degrees. It is a very familiar rule. So AB is the diameter of the semicircle. So AB is the diameter of the semicircle. It is absolutely a straight line. Okay, AB is a straight line as a diameter, a semicircle. It's the diameter of the semicircle. So if we focus on the upper side of the straight line AB at point O, according to the rule that I mentioned, the sum of the angles on one side of a straight line is equal to 180 degrees. The sum of the angles on the upper side of the straight line AB at point O must be equal to 180 degrees. So which angles we have at the upper side of AB at point O? We have this angle that is equal to 90 degrees plus the missing angle. In total, according to the rule that I mentioned, in total those two angles must be equal to 180 degrees. So therefore, this angle must be also equal to 90 degrees. In order to complete the sum of the angles on the upper side of the straight line O to 180 degrees, this angle must be equal to 90 degrees. Okay, so in the next step we'll focus on the right triangle EOB, and then we will implement the Pythagoras theorem on this right triangle EOB. So I will copy the right triangle EOB in a new page, and we will implement the Pythagoras theorem on this right triangle EOB. So this is the right triangle EOB. That I copied from the original drawing. Now we will implement the Pythagoras theorem on this right triangle EOB. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, EO square plus OB square equals to EB square. Okay. EO equals to square root of 5, so EO square equals to square root of 5 square. OB equals to square root of 10 units, therefore OB square equals to square root of 10 square. And it is equal to EB square. That is the square of the hypotenuse. Square root of 5 square is 5 plus square root of 10 square is 10. That is equal to EB square. 5 plus 10 is 15 equals to EB square. We found out that 15 equals to EB square. We'll take a root out of this equation and we'll find out that EB equals to the square root of 15. EB equals to the square root of 15. EB equals to square root of 15. The only thing that is left to find in order to find out the length of CB is to find out the length of line segment CE. In order to find out the length of line segment CE, we will complete the semicircle to a circle. Okay, we will do a construction. Okay, so we completed the semicircle to a circle. In the next step, we will extend line segment OE on both sides, in the upper side and in the lower side. Okay, we'll extend OE in the upper side until it touches the circle, and we will define the touching point of the extended line segment OE in the circle as point M. The next step, we will extend EO in the lower side until it touches the circle, and we will define the touching point of the extended EO in the circle as point N. Okay. What is line segment ON? point O is the center of the circle. Point N is the point of the circle itself. That is exactly the definition of a radius. That is to say, ON is the radius of the circle. We have already found out that the radius of the circle, that the semicircle is the same, equals to square root of 10 units. What is the length of OM? Again, point O is the center of the circle. Point M is the point on the circle itself. That is exactly the definition of a radius. That is to say, OM is the radius of the circle that is equal to square root of 10 units. OM equals to square root of 10 units minus OE. OM minus OE equals to ME. OM equals to the square root of 10 units minus OE, that is equal to square root of 5 units, equals to ME. Okay, MO minus EO equals to ME. MO equals to square root of 10 units, EO equals to square root of 5 units, therefore MO, that is square root of 10 units, minus EO, that is square root of 5 units, equals to ME, that is to say, ME equals to the square root of 10 units minus square root of 5 units. Okay, and we have already found out that ON equals to square root of 10 units, that is to say, it is the radius of the circle. In the next step, I will present to you a new rule. It is true in any circle. If we have this circle, it could be any circle. And this circle I will call chord AB. This is chord AB. I will draw another chord, chord CD. So in this circle we can see that chord AB intersects with chord CD, and the intersection point, we define the intersection point as point O. So according to the following rule, if chord AB I write in the black color, so it is, you can see it's better. If chord AB intersects with chord CD, and the intersection point is point O, at point O, then the following rule is true, the following equation is true. That is to say, AO times OB equals to CO times OD. I repeat again the rule. If chord AB intersects with chord CD at point O is the intersection point of chord AB with chord CD, then according to this rule, we will get that the following equation is true, that is to say, AO times OB equals to CO times OD. We can implement this new rule in our drawing. Why? Because in our drawing we have chord MN that intersects with chord CB at point E. So draw again the drawing in order to see exactly the two chords that intersect with each other. You can see here that chord MN, this chord that passes through the center of the circle. Intersects with chord CB at point E. This is called CB. And the intersection point is here at point E. So I write it down in our original drawing. Chord MN intersects with chord CB at point E. Point E is the intersection point of chord MN with chord MCB. Okay? Therefore, according to the new rule, we will get that ME times EN, ME times EN equals to CE times EB. Again, ME times EN equals to CE times AB. We have already found out that ME equals to the square root of 10 minus the square root of 5, while EN, you can see here that EN equals to EO plus ON. That is to say, EN equals to EO, that is square root of 5, plus ON, that is square root of 10. In total, EN equals to the square root of 10 plus square root of 5. And we have already found out that EB equals to the square root of 15. Okay, now we put the data inside the equation and we find out the missing chord CE. ME equals to square root of 10 minus square root of 5. Times EN. EN equals to square root of 10 plus square root of 5. And it is equals to CE, that is the missing line segment, times EB, that is equals to square root of 15. According to the formula that, to the algebraic formula that A plus B times A minus B equals to A squared plus B squared. Here A equals, we have square root of 10 minus square root of 5 times square root of 10 plus square root of 5. Here A equals to the square root of 10, B equals to the square root of 5. That is to say, A plus B times A minus B equals to A squared. A squared is 10, because it is square root of 10 squared, that is 10, minus square root of 5. Square root of 5 is 5. So 10 minus 5 equals to CE times square root of 15. 10 minus 5 is 5. That is equals to CE times square root of 15. We divide this equation by square root of 15, and we will get that CE equals to 5 over square root of 15. CE we see 9 segment CE equals to 5 over square root of 15. We have to find out the length of CB here. CB, it is very easy to see from the drawing that CB equals to CE plus EB. CB equals to CE plus EB. We are looking for the value of line segment CB that is equal to CE plus EB. CE plus EB. We just right now found out that CE equals to 5 over square root of 15 units plus EB. We already found out that EB equals to the square root of 15. So we found out that CB equals to 5 plus square root of 15 plus square root of 15. We divide square root of 15 by 15 and we multiply it by 15 in order to have a common factor with 15 over square root of 15. CB equals to 5 over square root of 15. So we will multiply square root of 15 by square root of 15 and then we will divide it by square root of 15. So we shall find out that CB equals to 5 plus square root of 15 plus square root of 15 is 15 over square root of 15. 5 plus 15 is 20, so CB equals to 20 over square root of 15. Now we will divide this number 20 over square root of 15 by 15 and then we will multiply it by 15, so we change nothing. And CB equals to square root of 15 over square root of 15. We multiply something by 1, so we change nothing. Times 20 over square root of 15. So we found out that CB equals to square root of 15 times 20 over square root of 15 times square root of 15 is 15. We'll divide this number by 5, both the numerator and the denominator, and we find out that CB, the line segment that we are looking for, equals to square root of 15, 20 over 5 is 4, and 15 over 5 is 3. So we found out actually that the line segment that we are looking for, that is to say CB, equals to the square root of 15 times 4 over 3. In terms of numbers, it is equals to 5.164 units. Okay, so that is the answer to the question, that the length of line segment CB equals to either square root of 15 times 4 over 3 or in terms of numbers, it is equal to 5.164 units. Okay, so in the next step, I'll summarize the lecture. Okay. Okay, again on the question. In the original drawing, we have a semicircle. Inside this semicircle, we have square DEFO. We know that the area of square DEFO equals to 5 units. And we have to find out the length of line segment CB. Okay, so first of all, we know that all the angles inside square DEFO are right angles. So all those 4 angles are right angles. And you know that the area of any square is equal to the side squared. The area of square DEFO equals to the side squared. And we know that the area is 5, so we can write down that the side squared equals to 5 square units. We took a root out of this equation and we found out that one side of square DEFO equals to the square root of 5 units. Okay, here all the sides of a square are equal to each other, therefore all the sides of square DEFO equals to square root of 5 units. Okay. In the next step, we join points O and D together by a straight line. So, as I already mentioned, point O is the center of the semicircle. Point D is a point on the semicircle itself, therefore triangle FDO. Therefore, DO is the radius of the semicircle, and triangle DFO is a right triangle. Why? Because this angle is 1 out of 4 angles of square DEFO, therefore it is a right angle. So I copied triangle DFO, the right triangle DFO, in this page. This is triangle DFO that I copied from the original drawing. We have already found out that DF and FO, they are both the sides of square DEFO, therefore they are equal to square root of 5 units, as we have already found out. This angle equals to 90 degrees because it is 1 out of 4 angles of square DEFO, therefore it must be a right angle. We implemented the Pythagoras theorem of the right triangle DFO. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, DF square plus FO square. That is equal to the sum of the squares of the perpendiculars equals to the square of the hypotenuse, that is DO square. So DF square plus FO square equals to DO square. DF square plus FO square equals to DO square. DF equals to the square root of 5, therefore DF square equals to the square root of 5 units, plus FO equals to the square root of 5, therefore FO square equals to the square root of 5 units, and is equal to the square of the hypotenuse, that is DO square, that is the missing side of this triangle, that is the hypotenuse. Square root of 5 square is 5, therefore we get here that 5 plus 5 equals to DO square. 5 plus 5 is 10, so 10 equals to d all square. It is the square of the hypotenuse. We took out of this equation and we found out that dO equals to the square root of 10 units. The hypotenuse equals to the square root of 10 units. But dO, what is dO? So what I mentioned before here, O is the center of the semicircle, D is the point of the semicircle itself. That is exactly the definition of a radius. So it is not only the hypotenuse of the triangle, the right triangle DOF, but it is also the radius of the semicircle. So we found out that the radius of this semicircle is equal to the square root of 10 units. But for the same reason, exactly, AO, what is AO? O is the center of the semicircle. A is the point of the semicircle itself. Therefore, AO is the radius of the semicircle that is equal to square root of 10 units. And for the same reason, exactly OB is also the radius of the semicircle. Point O is the center of the semicircle. Point B is the point of the semicircle itself. Therefore, OB is the radius of the semicircle that is also equal to square root of 10 units. Okay? Now we also know that AB is the diameter of the semicircle. AB is the diameter of the semicircle. It is absolutely a straight line. AB is a straight line, and we have the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. AB is a straight line, it's the diameter of the semicircle, therefore it is absolutely a straight line. So if we focus on the upper side of the straight line AB at point O, the sum of the angles on the upper side of AB at point O must be equal to 180 degrees. So which angles we have at the upper side of AB at point O? We have this angle that is equal to 90 degrees, plus the missing angle. In total, they must be equal to 180 degrees according to the rule that I mentioned. So the missing angle, that is to say angle MOB, must be equal to 180 degrees in order to complete the sum of the angles at the upper side of AB at point O to 180 degrees. This angle must be equal to 90 degrees. And because of the fact that this angle is a right angle, therefore triangle EOB is a right triangle. Therefore we can implement the Pythagoras theorem of the right triangle EOB. According to the Pythagoras theorem, I copied the right triangle EOB in the new page, and we implemented the Pythagoras theorem on this right triangle, triangle EOB. By PT is the equation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, EO square plus OB square equals to EB square. EO square plus OB square equals to EB square. EO equals to square root of 5 units. OB, it is the radius of the semicircle that is equal to square root of 10, therefore EB square equals to the square root of 10 units. And it is equal to EB square, the square of the hypotenuse, that is the missing side. So we found out that square root of 5 units plus square root of 10 equals to EB square. Square root of 5 is 5, square root of 5 square is 5, the square root of 10 square is 10, and it is equal to EB square. 5 plus 10 is 15, so 15 equals to EB square. We took a root out of this equation and found out that EB equals to the square root of 15 units. That is to say, the hypotenuse equals to the square root of 15 units. So we found out that EB equals to the square root of 15 units. Okay, in the next step, we actually completed the semicircle to a circle, and then we extended line segment EO on both sides, in the upper side and in the lower side also. We extended OE in the upper side here until it touches the circle at point M. The touching point of the extended OE in the circle is at point M. Then we extended EO in the lower side until it touches the circle at point N. Point N is the touching point between the extended EO and the circle. Okay. Then I presented to you a new rule. According to the new rule, if that is true in any circle, this circle could be any circle. If chord AB intersects with chord CD at point O, point O is the intersection point of chord AB with chord CD, then the following equation is true, that AO times OB equals to CO times OD. Okay, again, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. We can implement the new rule in our drawing. Why? Because in our drawing we have chord MN that intersects with chord CB at point E. Okay, therefore, so I copied the drawing again. Here. Chord MN intersects with chord CB at point E. Point E is the intersection point of chord MN with chord CB. Therefore, according to the new rule, we will get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. We have already found out that ME equals to the square root of 10 minus square root of 5. We found out that EB equals to the square root of 15. And actually, what is the length of EN? EN equals to EO plus ON. Again, EN equals to EO plus ON. That is to say, EN equals to EO, that is square root of 5 units, plus ON, that is square root of 10 units. In conclusion, we found out that EN equals to the square root of 10 plus square root of 5. Okay, so we substituted ME by square root of 10 minus square root of 5. We substituted EN by square root of 10 plus square root of 5. And it is equal to CE, that is the missing line segment, times EB, that is equal to square root of 15 units. So we have here square root of 10 minus square root of 5 times square root of 10 plus square root of 5. So, and according to the algebraic identity, that A plus B times A minus B equals to A squared plus A squared minus B squared, of course. Again, A plus B times A minus B equals to A squared minus B squared. And in our specific equation, we know that A equals to the square root of 10 and B equals to the square root of 5. Therefore, A plus B times A minus B equals to A squared. A is square root of 10, therefore A squared is 10. Minus B squared. B equals to the square root of 5, therefore B squared is square root of 5 squared, that is 5. So, in conclusion, we found out that A squared minus B squared equals to 10 minus 5, that is equal to CE times square root of 15. 10 minus 5 is 5, so we found out that 5 equals to CE times square root of 15. So we divided this equation by square root of 15, and we found out that CE equals to 5 over square root of 15. And we are looking for the length of CB. You can see from the drawing that CB equals to CE plus EB. Again, CB equals to CE plus EB. So CB equals to CE, we just right now found out that CB equals to 5 over square root of 15 plus EB. We have already found out that EB equals to square root of 15. So the answer to the question is that CB, the line segment that we are looking for, equals to 5 over square root of 15 plus square root of 15. Here we simplify this expression by multiplying square root of 15 by 15 and then we divide it by 15 in order to have a common factor with this expression. So 5 over square root of 15 plus square root of 15 times square root of 15. Again, here we multiplied square root of 15 by square root of 15 and then we divide it by square root of 15. We change nothing when we multiply anything by 1, so it is allowable. And here we have 5 plus square root of 15 times square root of 15 is 15. So we have 5 plus 15 over square root of 15. 5 plus 15 is 20 over square root of 15. So we found out that CB equals to 20 over square root of 15. Then we multiplied this expression by square root of 15 and then we divided by square root of 15 in order to eliminate the square root in the denominator. Again, we divide it by square root of 15 and then we multiply this number by square root of 15, so we change nothing because we multiplied by 1. And we got here square root of 15 times 20 over square root of 15 times square root of 15. So in the numerator we have square root of 15 times 20. In the denominator we have square root of 15 times square root of 15. Square root of 15 times square root of 15 is 15. Okay, so we found out that CB equals to the square root of 15 times 20 over 15. Then we divided this equation, both the numerator and the denominator, by 5. And found out that 20 over 5 is 4 and 15 over 5 is 3. So in conclusion, we found out that CB equals to square root of 15 times 4 over 3 units, or in terms of numbers, here this line segment CB or chord CB equals to either square root of 15 times 4 over 3 units, or in terms of numbers, it is equals to 5.164 units. Okay, thank you very much.